Hello everyone, for this tutorial video I'd like to explain how you can use calculus techniques on vector functions, such as finding limits, derivatives, and integrals. If we have the three components having one argument of t, then it follows the limit as t approaches a would be the limits of the individual components, which if you are unsure about why this works, you can convince yourself this is true by sketching a graph of one of the vector functions in the last video and taking the limit at a specific value, and it will work whether it is in 2 or 3 dimensions. Since we know from Calculus 1 the definition of the derivative involves a limit, it should not be too surprising that the derivative of a vector function is simply the derivatives of the individual components. And we can also see the basic derivative rules of single variable functions hold true for vector functions as well. For example, the derivative of a sum is the sum of the individual derivatives, which makes sense because of how vector addition works. The derivative of a constant times a vector function is simply the constant times the derivative of the vector function by itself, which makes sense if you know how multiplying vectors by constants works. The derivative of a product of vectors is the derivative of the first vector times the second vector plus the derivative of the second vector times the first vector, which is simply the product rule, but using vector functions instead. So if we have the vector of a cross product or dot product, we use the product rule in the same way, i.e. taking the derivative of one function, keeping the other function the same, repeating the process, and then adding the two results. And finally we have, by the chain rule, the derivative of a vector function with a function as an input rather than a scalar is the derivative of the vector function with the function as the input times the derivative of the function. With all that out of the way, we first have to define what continuity is for vector functions, and this is called a smooth curve, which means it is continuous everywhere except possibly at the endpoints, but it cannot have any discontinuities between these two endpoints. A helix being a good example of this point. Since we remember the function has to be continuous for there to be an integral, that is why we stopped to define continuity for vector functions first. Since we know the derivative of a vector function is the derivative of the individual components, the same thing should hold true for the antiderivative, although the catch here is that the constant of integration is a vector rather than a regular number or scalar. Since we know this is true for antiderivatives, it should follow that this is true for definite integrals as well, because of the fact a definite integral is the antiderivative at the endpoint minus the antiderivative at the beginning point. In conclusion, the definite integral from point A to point B, or from beginning to end, must be the definite integral on the same points in all the components individually. Now that we have figured out how to apply calculus techniques to vector functions, we can discuss special vectors that use calculus techniques, such as tangent lines or normal lines, in the next video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.